Welcome back. In our last video, we discussed on the concept of continuity. We also took an example to that effect. This time around, we want to look at the concept of differentiability of a complex function, how it is defined, and of course, how we can solve questions based off it. Remember, if a function is differentiable, then that function will be continuous. As always, make sure to like, share, and subscribe. And make sure to turn on your notifications so you are alerted whenever a new video comes up. So let's begin. First and foremost, let us define for ourselves a complex function f of z. Then we will say that f of z is differentiable at a particular point z0 if w prime can be written as f prime of z0, which we can write as the limit as delta z tends to 0 of f of z0 plus delta z minus f of z0 divided, of course, by delta z. Now, of course, by this notation, we are saying that delta z is equal to z minus z0, of course, for a specific point z0, which means that we can write f prime of z0 as the limit as z tends to z0 of f of z minus f of z0 divided, of course, by v minus z0, right? So we can either decide to write the function in this nature, or we can decide to write the differential in this nature. Either one is fine. Now, of course, based off this, we can then create for ourselves an epsilon delta definition to this effect, and we can say that alternatively, right, we can say that for all epsilon greater than 0, there is, of course, a delta which is greater than 0, such that, in this case, if you write it as delta z, we have that delta z less than delta would imply, of course, that the absolute value of f of z0 plus delta z minus f of z0 divided by delta z minus f prime of z0 will, of course, be less than epsilon, right? Will, of course, be less than epsilon. And, of course, you could also write it in terms of the other function as the case is. Or, for epsilon greater than 0, there is a delta greater than 0 such that z minus z0 less than delta would imply that f of z minus f of z0 divided by z minus z0, of course, minus f prime of z0 will be less than epsilon. Either one is fine. This is how the differentiability of a complex function is defined. Now, we can use this extensively in a lot of ways. We can use this to discuss the differential of different kinds of functions in different stages. Now, remember that this is a limit case, which means that for the differentiability of that function to hold, or for the differential to exist, it makes sense that the limit of this function must be consistent and must be the same across any axis we decide to evaluate the function on. Now, we will see what this means with a simple example. Let us look at something like this. Now, let's take a look at a function like this. We are to discuss the differential of f of z, which is equal to 4x plus y plus I into minus x plus 4y. Of course, in this case, this is, of course, our real part, and this is, of course, the imaginary part. Now, we have these two parts. We are just going to leave it like this. Now, we have to define or discuss this function based off these two parts of the function. So, how exactly can we proceed as quickly as we can. Now, based off this, we can write this in terms of f of z naught as the case is. Then f of z naught, of course, can be written as 4x naught plus y naught plus I minus x naught plus 4y naught, right? Since, of course, f of z is equal to f of x comma y, right? Of course, the same notation. Remember, we started with that. We said that we could write it as a function of just one single complex variable or a function of two real variables where x is the real part and y is the imaginary part. So that same thing applies for f of z naught, which would mean immediately that f of z naught plus delta z can also be written in such a nature, which means I can have this to be 4x naught plus 4 delta x in this case, right? Same notation as necessary. You could decide to write it based off this or not, right? Now, of course, based off this notation, you realize that we would be using the fact that delta z is the one tending to 0. So we are using the first form of the limit, no issues. And then we have plus y naught plus delta y. In this case, that's changing y. So that works for the real part of the function. And then we evaluate the same thing for the imaginary part of the function as the case is. So we can have that written under as plus I minus x naught plus delta x plus 4y naught plus delta y. Now, we can, of course, split this out in full and see what we have. You would have this to be 4x naught plus 4 delta x plus y naught plus delta y, right? Now, if we open this bracket as necessary, we'd have minus I x naught minus I delta x, right? Plus 4I y naught plus 4I delta y. This is what we are going to have. Now, let us try to compare and collect like terms where necessary so we can see what part of the functions we have. Now, if we wish to do this, we see something very, very interesting as the case is. We realize that from this case, you have 4x naught plus y naught, right, which is the real part of f of z naught. Then you have minus x minus I x naught plus 4iy naught, which is going to give you the imaginary part of f of z naught. So that tells you that f of z naught is still present within the process. Now let's put this all together and you realize exactly what this means. It implies immediately that if we were to take f of z naught plus delta z minus f of z naught in this regard, what will happen is that we are subtracting this function from this. So 4x naught will cancel, y naught will cancel, minus iy naught minus ix naught will cancel, and then 4iy naught will also cancel. So what will be left in this case is just going to be 4 delta x plus delta y minus I delta x plus 4I delta y, which means immediately that, of course, if we write f of z naught plus delta z minus f of z naught divided, of course, by delta z, we will have, in this case, 4 delta x plus delta y, right, minus I delta x plus 4I delta y, all divided by delta z, which we can write, of course, as delta x plus I delta y. Now, this is very, very interesting to keep in mind. Now, you realize that, of course, this is definitely a change in the function itself, right? So we can write this for notation's sake as changing f divided by changing z. Okay, so now we've been able to first and foremost start off with the notations as far as this is concerned, right? This is all well and good. Now, based off this notation, the question now arises that how exactly can we utilize this concept? Can we use this to evaluate the differential? Now, we can evaluate this differential along different directions. We can start off by evaluating this along the real axis, or we evaluate it also along the imaginary axis, and we can also evaluate it along the line and see if the limit values we obtain along this different axis is the same. If we see that the limit is the same, then it means that that function will definitely be differentiable, and we will be able to find the differential, which will be the value of the limit. We will do this in our next video. Of course, what we have covered today is the definition of the differential, and we have started off with an example. In our next video, we will complete this example and see exactly how well we can solve based off this concept. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss our next video. Thank you.